All right, in this big ideas tutorial, section 10.6 for the geometry, segment relationships in circles. So we're going to talk about segments of chords, tangents, and secants. So those are all different lines that could happen intersecting inside, outside, and through your circle. So when you have two chords that intersect the interior of the circle, those chords are going to be divided into different segments, and those are just called segments of the chord. So like this diagram below, you have chord AB crossing chord CD, and there's 4 different segments right there. So if those two chords intersect in the interior, the product of the lengths of the segments of one chord is equal to the product of the lengths of the segments of the other chord. So that sounds kind of wordy, but we're going to go through this piece by piece. So you have 4 different segments. Mainly, you have segment AE and EB, where that is being cut through segment CD. Those two things get multiplied together. Those are also going to be equal to the other 2 segments, which are CE and CD. So on the same chord, if you multiply both of those segments together, they're going to equal the multiplication of the other 2 segments together. So as long as you're staying consistent with which chords you're multiplying and which segments together, as long as you're on the same chord. Okay, so we're going to look at this together. Find the ML and find the JK. So given that we have x plus 2 and x plus 1 as one segments, x and x plus 4 as the other ones. So we're going to look at the individual segments and pair them up together in a multiplication problem. So NK is your x, NJ is your x plus 4. Those two go together. NL is your x plus 1, NM is your x plus 2. Those two things go together. So notice how you're staying on the same chord, same chord. And then you're just going to follow your rules of algebra. So in this first one, you're going to distribute. X times x is x squared, x times 4 is 4x. And then for the second one, you're going to multiply those binomials by either foiling or using the box method to get x squared plus 3x plus 2. Combining like terms, you have 2 x squareds together that can be canceled or subtracted onto both sides. Combining like terms with your x's and moving the 3x over to the left, you just get x equals 2. You then have to simplify and find that x into your ML and then into your JK. So since ML is x plus 2 and x plus 1, you're going to combine all of those together with the addition and substituting your 2 into the x. When you add that all up, you get 7. Then your JK, you do the same thing. Add the 2 segments together, but instead of your x, you're using 2, and you get 8. All right, tangent segments. So tangents are outside of your circle. If those tangent segments meet at a same endpoint, they're tangent segments. Secant segments contain the chord of the circle that has exactly one endpoint. So notice how this black part right here, you're crossing 2 points of the circle, so it becomes a secant. But for the blue one, you're only crossing at 1 point, so it's a tangent. So anytime you have an exterior part of this secant, it is called an external segment. So when we move on to the next one, we're looking at both secant segments. So secant segments that are meeting on the outside of the circle but crossing the circle twice. The product of the lengths of one secant segment and its external segments equals the product of the lengths of the other secant segment and its external segments. So again, looking at these individually, so your EA in red, which is the external secant of the first one, times the whole secant, which is your EB, so the external times the whole, is going to be equal to the external times the whole. So it's not like the chord one where it's just each individual part. For your secant, it's external times whole, external times whole. So let's look at these for this first example. These are both secants. They're crossing the circle twice. So the secant proportion formula is external times whole, external times whole. RP times RQ, RS times RT. Substitute those in. The whole thing is 9 plus 11. The whole thing is 10 plus X. Then you're just going to simplify. You can do PEMDAS in here first, so you would get 20 times 9 to get 180. And then to do the 10, you would distribute because you have your variable. Subtract 100 on both sides to get 80, and then you divide by 10 to get X equals 8. All right, moving on to a combination of tangents and secant segments. So if a secant segment and a tangent segment share an endpoint outside the circle, then the product of the lengths of the secant segment and its external segment equals the square of the tangent segment. So the top one, which is blue, is a tangent because it's only crossing once. The bottom one is a secant because it's crossing twice. So EA times itself is going to be equal to external times whole. Because remember, this is a secant, so it's always external times whole. And it's just tangent times itself, tangent. You could either square it or you can multiply it twice. It's going to be the same thing. So let's look at this example, looking at finding RS, which is going to be this X segment. So RQ is a tangent, RT is a secant. So we're going to be tangent times tangent, external times whole. So RQ times itself, external times whole. Plugging in for RQ is just 16 squared. RS is our X, RT is X plus 8 because it's the whole. Distribute and simplify. 256 equals X squared plus 8X. Then we're going to write this equation in standard form by taking the 256 over to the right-hand side and then using the quadratic formula to solve. Plugging in for negative b plus or minus the square root of b squared minus 4ac all over 2a, and simplifying that down, you get negative 4 plus and minus 4 times the square root of 17. So we're going to use the positive solution because lengths cannot be negative. Previously, we've talked about how square roots can be both positive and negative. So this is the situation where this is coming up, both positive and negative. You cannot have a negative length, so we're going to be using the positive. And you simplify that down to get approximately 12.49 in terms of a real number. So in this example, you can draw different segments of QS and QT to connect them to create a triangle. And you have your reflexive property of congruence, where your angle of QRS is going to be congruent to TRQ because of triangle congruency theorem based on angle-angle similarity. And you could also write that as a proportion of x 16 and 8 over whatever your SQ length is going to be to get your x. It would just be a different way if you don't like the quadratic formula. All right, so now we're going to find the radius of an aquarium tank. This is a real-life problem. Your radius is indicated here as 2 different r's, but drawn as a diameter, because diameter is 2 times the radius. Then you have an external segment of 8, and then you have a tangent of 20 feet. So since this is tangent and secant, we're going to do external times whole and tangent times tangent. So that's the CB squared, which is 20, CE is 8, and then CD is 8 plus R, or 2R, which is your diameter. 20 squared is 400. Then we've got 16R plus 64. Move the 64 over on both sides, 336. And divide by 16 to get 21 as the radius of the aquarium.